This video is about kinetic molecular theory and ideal versus real gases. By the end of this video, you should understand what kinetic molecular theory, or KMT, refers to. You should be able to explain the main tenets of KMT in terms of particle behavior. You should understand why real gases deviate from ideal behavior. And you should understand the conditions under which real gases deviate most from ideal behavior. Before we get into the specifics of kinetic molecular theory, it's important to remember what we mean when we talk about models. Kinetic molecular theory is a model that will help us explain gas behavior. A model, as we've seen before, is an approximation. It's successful in that it explains observed behavior. However, it should not be taken literally. As we'll see, some of the assumptions of kinetic molecular theory are actually false. However, under most conditions, even these false assumptions help us explain and predict the behavior of gases. Let's take a look at each of the tenets of kinetic molecular theory individually. First, KMT tells us that gases consist of large numbers of molecules that are in continuous random motion. Here we see gas particles in this box. As we know, gas particles are constantly moving and their paths are random. They usually continue in a straight line until they hit something like the walls of the container or each other. Likewise, as we've seen before, gas pressure is the result of the collisions of these gas particles with the walls of their container. Recall that pressure is force over area, so we're looking at the force of the particles hitting the container over the area of that container. The next tenet is that the combined volume of all the molecules of the gas is negligible relative to the total volume in which the gas is contained. Recall that we measure the volume of the gas based on the volume of its container, since a gas will occupy the entire volume of its container. It turns out that the particles are so far apart that we can actually consider the volume of the individual particles to be negligible as compared to the volume of the gas itself. Consider the diagram shown here. The volume of the gas is the entire square, since it will take up its entire container. If we consider the volume of this entire gas versus the combined volume of just each of the particles represented in red, we'll see that the volume of the particles is negligible as compared to the volume of the gas. Negligible, of course, means that it's small enough that we can ignore it under most conditions. However, it does not mean that their volume does not exist at all. The next tenet of kinetic molecular theory is that the attractive and repulsive forces between gas molecules are negligible. This again is the result of the large distance between gas particles. Since gas particles are so far away from each other, they do not interact in ways that attract or repel. Consider Coulomb's law, as we've seen before. As the distance between the particles increases, the force between them, whether attractive or repulsive, decreases. The next tenet refers to the average kinetic energy of the molecules. So long as the temperature of the gas remains constant, the average kinetic energy of the particles will remain constant with time. However, energy can be transferred between molecules or particles during collisions. When one particle hits another particle, some of its kinetic energy is transferred to the particle it collides with. However, on average, the kinetic energy remains the same. Our final tenet is that the average kinetic energy of the particles is proportional to the absolute temperature being the Kelvin temperature. Here we see that the average kinetic energy is probably somewhere in this region for 0 degrees Celsius. As we increase the temperature, we also increase the average kinetic energy of the particles, which is again somewhere around the peak of this curve. Note that this does not mean that all of the particles have identical speeds. Rather, it means that on average they have the same kinetic energy. Some will have more and some will have less. Kinetic molecular theory, as we've just described it, does an excellent job of describing how an ideal gas would behave. However, consider the graph below. For an ideal gas, PV should be equal to nRT. So if we divide these two values, we should get a value of 1, as represented by this dotted line here. Here we've looked at this ideal value as we change the pressure of the gas. Again, if the gas behaved ideally, the increasing pressure would not change this value of 1. However, with real gases, as shown here, we see large deviations from this value of 1 as our pressure increases. Therefore, in the real world, the behavior of gases does not conform to the ideal gas equation, particularly at very high pressures. However, rest assured, we can still use the ideal gas equation under most conditions. Consider this portion of the graph here that we've zoomed in on. This tiny little gray box is zoomed in on right here. Notice that below 1 atm, we have very, very ideal behavior. Even between 1 and 2 atm, our gases behave relatively close to an ideal gas. Now consider the fact that we really only ever work at pressures around 1 atm or lower. Therefore, the ideal gas equation will describe gases under conditions of low pressure very, very well, and we usually only look at conditions of low pressure. So we shouldn't worry too much about this, but we do need to explore why this occurs. Before we get into the why, let's look at a single gas at different temperatures and pressures. Here again, an ideal gas would give us a value of 1 if we divided PV by nRT, represented by the dotted line. However, this real gas deviates greatly as pressure increases and temperature decreases. Notice that the higher temperature line is actually closer to ideal behavior than the lower temperature line. Therefore, we see that gases behave ideally at low pressures and high temperatures. Let's explain this in terms of particle behavior. Think back to the assumptions we laid out about kinetic molecular theory, particularly the assumptions that the volume of the gas particles are negligible and they do not attract each other. Both of these assumptions were based on the fact that the particles in a gas are very, very far apart, meaning the volume of the container is much larger than the volume of the particles themselves, and the particles are so far away that they don't actually interact with one another. However, at very high pressures and low temperatures, our particles begin to get closer and closer together. Therefore, these assumptions start to break down. Suddenly, the volume of the actual particles does start to matter, as compared to the volume, which is now smaller, of our entire gas, represented by the volume of the container. Likewise, as the particles get closer together, they do start to attract and repel each other, since according to Coulomb's law, as distance decreases, the force between the particles increases. So, in summary, gases will deviate most from ideal behavior at high pressures and low temperatures, because the volume and the interactions between the particles start to matter as they get closer together. Likewise, gases that deviate most from ideal behavior are gases with large molar masses, due to the larger particle volume, and gases with strong intermolecular forces, due to the non-negligible particle interactions. That brings us to the end of this video. Let's review our goals. First, we looked at what KMT refers to. Then we explained the main tenets of KMT in terms of particle behavior. Then we looked at why real gases deviate from ideal behavior and the conditions under which real gases deviate most from ideal behavior.